Hello, everyone. Welcome back to our lecture series. Emeka Udenze is speaking once again. Today we'll be looking into Introduction to Lipids and Fatty Acids. Remember, we're still talking about the biochemistry part of this GOB lecture series. Now, let's take it off from there immediately. I have a quote here this time. It's an African proverb that says, "An ant on its feet can do more than an elephant lying down." African proverb. This is just a food for thought. I'm not going to say anything about it. We're going to immediately take off with our lectures. Here, first of all, the learning objectives. Today, we have a few learning objectives to iron out. Number one, we're going to classify lipids based on their complexity and saponifiability. That's what we're going to do. We're going to describe the functions of lipids, and then we'll describe the general characteristics of fatty acids, which are part of the building blocks of lipids. And then we'll now know how to draw the structural formulas of a few of them that you need to know, particularly for your assessment, for your quizzes and exams. The stearic acid, oleic acid, linoleic acid, and linolenic acid. We're going to talk about the characteristics of each of these fatty acids. Let's immediately take off the lecture. Lipids. What are lipids? Lipids can be described as a diverse group of biomolecules, of course, biomolecules that naturally occurring, particularly in living things, living organisms, that are non-polar. They are non-polar. That means they are hydrophobic in nature. What that simply shows is that lipids are soluble in organic solvents. They're soluble in organic solvents such as diethyl ether and acetone, and insoluble in water. Water is a polar, so they're insoluble. That's why they're hydrophobic. They're hydrophobic because they're insoluble in a polar solvent like water, but soluble in non-polar solvent like diethyl ether, acetone, and a list of other ones like chloroform and all the rest of them. Now, lipids are generally amphipathic. Particularly when we start talking about particularly the simple class where we have the fatty acid. They're amphipathic. Amphipathic is the way you describe a molecule or a compound that has one part of it to be polar. One end of it is polar and water soluble, whereas the other end is non-polar and water insoluble. So if you have a molecule that has, assuming we have a molecule now, this part is polar and water soluble, and the other part is non-polar. We now describe that compound as an amphipathic. So we're going to be hearing a lot of this in this, so it's important we know that meaning. So lipids can be classified in many ways. I'm going to show you about 3 classifications, which the 3 classifications have close links to each other. But it's important we look at them very well. Now, according to their complexity on their composition, they can be classified as simple lipids. Simple lipids are made up of triacylglycerol or triglycerides and waxes. You can say TG usually. I like calling them TG, triglycerides and waxes. Now, the complex lipids are usually the phospholipids, or you call them the glycerophospholipids, and then the sphingolipids. There are phospholipids are constituted of the glycerophospholipid, those of them with glycerol, and then the sphingophospholipid. Sphingophospholipid has phosphate group and sphingosine. We're going to talk about this. And then the glycolipids. Now, the steroids are just derivative of cholesterol. The steroid means they are made from the cholesterol nucleus. Cholesterol is their parent compound. So here we're going to be looking at the cholesterol, the steroid hormones, and then the bile acid. And finally, the eicosanoids. The eicosanoids are derived from arachidonic acid. Arachidonic acid is an unsaturated 20-carbon fatty acid, and they are like the precursors of these 3 eicosanoids: the prostaglandins, the leukotrienes, and the thromboxanes, which we're going to talk about by the time we move on in this class. So now we can also look at the first class we did is according to their composition. This is according to their composition, actually, or complexity. Now, if we want to do them according to whether they can be broken down, saponifiability has to do with the ability of a lipid to be broken down into constituent parts. into other smaller molecules. Now, so if a lipid saponifiable, a lipid that is saponifiable means can be broken down into other component units, including alcohol. You can break it down into alcohol, fatty acid, plus other molecules. Let's just say other molecules. You can break it down to these things, you know. So now, whereas those of them that are non-saponifiable, like this one, cannot be broken down. So the saponifiable one particularly constitute the simple and complex ones. So if you look at this now, these saponifiable ones was the classification we call the simple plus complex ones. So the simple and complex ones are all saponifiable, and they include the triglycerides, or triacylglycerol, TG, earlier I called it, the waxes, glycerophospholipid, sphingolipids, and glycolipids. Whereas those ones that cannot be broken down are usually the steroids. They are those ones that we put in those special classification, the steroid hormone, the bile acid, and then the eicosanoids. And then it went further to show you a graphic display of saponifiable lipids. So those saponifiable lipids, or you can say simple plus complex lipid. That's P didn't come out well. Let me write it. Okay, simple plus complex lipid. Now, this is the broad classification of what they look like. Those saponifiable lipids, because they include the simple and complex. Now, they're divided, of course, into the simple and the complex. I told you that. Then the simple ones involve just the triglyceride itself, which is the TG. Now, every triglyceride is made up of, the backbone is glycerol, and glycerol is the esterified to fatty acid, 3 fatty acid. So you have 3 fatty acid that is connected to glycerol through an ester linkage. That's an ester. We're going to look at that. Now, and the waxes. The waxes themselves, the difference between the waxes and the triglyceride is that the waxes here are made up of an alcohol. This time, the alcohol is not glycerol, but usually long-chain alcohols. Usually a long-chain alcohol and a longer chain fatty acid. And a longer chain fatty acid, which have their usual ester bond at this point. So this is an ester bond. So these are the two classes of simple lipid. That the complex lipid can be divided into the phospholipid and then the glycolipid. The phospholipid themselves can be divided further into two: the glycerophospholipid and the sphingolipid. The glycerophospholipid, glycero from the name, contains glycerol backbone, esterified to 2 fatty acids. However, the last ester alcohol group of the glyceride is connected to a phosphate group, and the phosphate group can now be connected to an amino alcohol. There are various amino alcohols that will be considered at the level of this class. They include the choline, the ethanol amine, and the serine, but we're going to talk about them when we get there. And then the sphingolipids do not have cholesterol. Instead, they have a long chain amino alcohol called the sphingosine. So the sphingosine itself is connected to a fatty acid through an ester bond here. This is an ester bond. And then the first alcohol there in carbon number 1 of sphingosine is connected to a phosphate group, and that phosphate group is also connected to a choline. A choline, like I told you, is the type of amino alcohol I mentioned here. It's the commonest amino alcohol. So this is what forms, this is the backbone of the sphingolipids, or you can call them sphingophospholipid. You can call them that sphingophospholipid. The sphingophospholipid. You can call them that. Whereas these ones, you can also call them phosphoglyceride. Phosphoglyceride. And then the last group of this complex lipid are the glycolipids. Now, the glycolipids themselves can also be called sphingoglycolipid. You can call them the sphingoglycolipids. Now, the sphingoglycolipids now contain the sphingosine backbone, which is the long chain carbon 18 unsaturated alcohol. Now it has connected to a fatty acid. Now in this case, the fatty acid here, okay, I think I missed something. Now I'm going to get back to it. The fatty acid connected here is not an ester bond. I'm going to work this back from here. This bond actually is an amide bond. Remember, this alcohol is a long chain amino alcohol that has 18. So this bond here is an amide bond, whereas this one is actually a glycosidic bond because it involves a carbohydrate. It has a fatty acid and a carbohydrate. And the carbohydrate here is usually glucose, galactose, or an oligosaccharide. So forming that glycosidic bond. Now, let me walk back this one. In sphingolipids here, now see. Now, this fatty acid does not have an ester bond here. Now, the carbon number 2 of this fatty acid, of sphingosine, has amino group. That amino group is connected to the carboxylic group of the fatty acid to form the amide bond, like I showed you here. So here, let me just write that, is an amide bond. Now, however, the phosphate group here forms a phosphate ester bond with the alcohol group in carbon number 1 of sphingosine, and then the phosphate group there also forms another ester bond with choline in the sphingolipid. So this is a general way to look at the saponifiable or the simple and complex lipid. Let's now begin to take it off immediately. What are the functions of lipid? Lipid have various functions, a couple of functions. Number one, let's talk about the number one, they repel water. In repelling water, they provide the protective wax coating that is found in some plant, and that provides a good protection for them. They are energy-rich compounds. Of course, they are used in storage of energy. They are useful storage forms of energy, both in plants and animals. And that energy is usually stored in terms of triglyceride or TG, or you can say triacylglycerol. Of course, when triacylglycerol is broken down, it releases a glycerol, which finds its way into the glycolytic pathway to be broken down to provide energy. And finally, later from there, it goes to the stearic acid cycle. The fatty acids themselves go into beta oxidation to release huge amount of energy. So they're a very good source, a very good storage form of energy, both in plants and animals. Now, there are also storage components of cell membranes. Yeah, there are storage components of cell membranes, and there are a lot of lipids that are that. They include the phospholipid, the triglyceride, the sphingolipids, and even the cholesterol are all part of the phospholipid bilayer. Now, they also constitute signaling molecules. They act as hormones, particularly signaling molecules or hormones. In prostaglandins and thrombocytes are highly bioactive. Not just that, even in steroid hormone, I should have added this, the steroid hormones, like the glucocorticoid and then the mineralocorticoid, the aldosterone, the cortisone, the progesterone are all signaling molecules. So lipids form important role in signaling. All right, and then transport molecules. In transportation molecules, lipids are transported in blood as lipoproteins. And lipoproteins, there are different types. There are the LDL, the HDL, the VLDL, and the chylomicrons. And finally, they also act as insulation in animal. Of course, they help to provide warmth for the animal, particularly the adipose tissue layer of the skin provide warmth for the animal, and that is an important function of the lipids. And of course, the adipose tissue is actually made up of triglyceride particularly. So now let's start talking about from the simple ones, fatty acids. Fatty acid are long chain carboxylic acid. Of course, anytime we see anything, they're organic acid, carboxylic acid, organic acid. So they must be known by having the COH, which is what? The carboxylic group. So of course, this is very common in all fatty acids. Now, of course, they are derived from the hydrolysis of both animal fats, vegetable oils, and then phosphoglyceride of biological membrane. So if you break the triglyceride down, now triglyceride, like I showed you earlier, remember when I showed this picture, the triglyceride is made up of fatty acid, 3 fatty acid, and glycerol. So if you break these ester bonds down, you're going to have fatty acid. So you get them from what? The hydrolysis of fatty acid and oil. Of course, fatty acid and oil, you can also call them lipids. And then, of course, what are their characteristics? They have long nonpolar tails that are responsible for most of the oil nature. The oiling or the fatty acid nature is the long nonpolar tails. The long nonpolar tails provides that hydrophobicity, whereas the carboxylic group is the polar head. The carboxylic group is the polar head, which is hydrophilic under physiological condition, and in fact exists as a conjugate base, which is an acid that has lost its proton. Now, of course, I said again, like I said generally about the lipid, they are amphipathic. Amphipathic is that one part of it is hydrophilic and the other part is hydrophobic, and that can be seen from this. Now, this is a fatty acid here. What is the number? Let me count. If we count from here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, so this is a C14 fatty acid, C14 carboxylic acid or fatty acid. Now, look at it. Now, this is the polar head. The polar head is made up of the carboxylic group, which is a COO. This is the polar head, carboxylic group. It is polar and hydrophilic. What it means is water soluble, whereas the rest of this part is the non-polar hydrophilic tail, which is water insoluble. So having both of these polar and head, the polar head and the non-polar head, is what makes this fatty acid amphipathic in nature. All right, let's move on. So they also form micelles. So what are micelles? We talked about micelles when last we talked about, I remember we talked about fatty acid too, when we talked about carboxylic acid too. So let's talk about them again. Of course, micelles are spherical cluster of molecules in which the polar heads are, or the polar chains, let's put it that way. The polar chains are on the surface and they are in contact with the aqueous. Aqueous means the water environment. Whereas the non-polar tails or the non-polar are located inside and they are held together by weak London dispersion forces. Of course, the formation of micelle formation and structure is very important in biological function, particularly in transport of lipids and even in the structure of the cell membrane. Structure of the cell membrane, because it is still this type of arrangement that forms the basis of what the cell membrane structure. So look at the micelle. Of course, the blue heads here are the polar head. This is the polar head that is what? Hydrophilic and soluble. Of course, outside here is surrounded by water molecule. Now, these tails are the hydrophilic tails. These tails are the hydrophobic. This is not hydrophobic or non-polar. Remember, this is the polar head or hydrophilic. Polar head or hydrophilic. This is the hydrophobic or the non-polar tails. Of course, outside here, this dot I tried to put shows you that there are water outside in the environment. So the formation of micelle is very, very important, particularly in physiological or rather biological processes, particularly all those structures that are based on lipids and fatty acids. Okay. So what are the characteristics of fatty acid? Let's try to know the characteristics of fatty acid. Now, fatty acid usually are straight chain. They are usually not branched. They don't have branching. They are usually straight chain carboxylic acid. They don't have any branching in them. They don't have any branching. Now, their size is usually range from 10 to 20. There could be other ones that are artificially synthesized that can be more than this, but generally their size ranges from 10 to 20 and usually even number. So you can have 10, 12, 14, 16, 18, 20. That is usually how the number goes. Now they can either be saturated or unsaturated. Of course, saturated means that all the carbon-to-carbon double bonds are single. All the carbon-to-carbon double bonds are single. Now, these saturated fatty acids are solid at room temperature. They're solid at room temperature. And because they are what? Because they are saturated, they pack together in such a way that it maximizes interactions by London dispersion forces. And because that interaction is maximized, they pack really well, they have high boiling and melting point compared to what? The unsaturated ones. Now, if you look at their packing, look at the packing here. Now, if this is a saturated acid, if you have another one, they pack really close. And because they pack really close, they don't have a lot of open spaces in them. So if I have my COOH here, another COOH, another COOH, another COOH. So these four molecules that are packing together. So this close packing is what makes them to become solid at room temperature, and usually they have higher volume and melting point than the unsaturated ones. The unsaturated fatty acid, on the other hand, contain at least one or more carbon-to-carbon double bonds, and usually of the cis configuration. The naturally occurring ones exist as only the cis configuration, and this has some consequences. What are the consequences? Look at the consequences. Now, the cis configuration creates a kink or a bend in the fatty acid chain, and this prevents them from packing. Now, they don't usually pack the way the saturated fatty acid does. These guys don't have, so their packing is not organized, and therefore they have a lot of open spaces. So because they have these open spaces when they pack, it leads to what? Weaker intermolecular forces, particularly London dispersion forces, and as a result they have lower melting point. So they are liquid at room temperature, and like they are liquid because of this, they are liquid at room temperature. And of course, the melting point decreases as the number of carbon-to-carbon double bond increases, the melting point decreases because it creates more spaces that they cannot pack. So the more the double bond, the more it creates those spaces, the more they cannot pack, and the more fluid they become. So the fluidity of the biological membrane is actually explained by the length of the chain and the presence of the double bond. So the more the double bond a biological membrane has, the more fluid it becomes. Now let's see. I drew the other one and showed you how the saturated ones, these are the saturated ones, how they pack. They are packing. Now what about the unsaturated ones? How do they pack? Let's see. The unsaturated ones, like I told you, the cis configuration provides this kink or bend. Now, so assuming I have one here, it goes this way. If I introduce only one of these, this is a cis configuration. Then you continue this way. Now, if you have another one, and then let's say it now packs here again, and then it now goes, okay, let me see. No, I don't want this. I want it back. Okay, it now goes this way. You see, you created another space just because of this kink. So this cis configurations is what brings that kink, the kink or bend, creating these spaces that you didn't see in the packing of the other ones. It is the creation of this packing space because of this bend, which is brought about by the kinks of the cis configuration, that makes them to be fluid and rather more or less liquid at room temperature. And as a result, they have low melting point compared to the saturated ones. So now let's look at that. Let's just look at the ones I drew with my software. You see, if this is a stearic acid here is a C18. If you count it, you're going to try to, now you can pause this video and count it yourself. This is a C18 carboxylic acid. And then it does not have, it is 18 sorry. What it means is that it has 18 carbons, it doesn't have any saturation. That means it doesn't have any unsaturation, it doesn't have any double bond. Therefore, it is what? It is a saturated fatty acid. As a saturated fatty acid, it is completely linear. There is no bend because it is the kink provided by the double bond that provides bend. So if you look at it, it's very long. There is no bend anywhere. So this is actually stearic acid. So this can easily pack itself together. Now, if you come to this one, now look at this one. This is oleic acid. Oleic acid is an unsaturated one because there is a what? A kink here. Look at the double bond. This double bond is creating a kink. Look at it. Look at this one. It's straight. This one is not linear anymore. It is bent. It is bent to the left a little bit, you see, because of this single kink here. Now, the unsaturated ones, this kink or bend, now it has 18 carbons again. It has, it has 18 carbons and one double bond. Here means 18 carbon and one double bond. This is oleic acid. So oleic acid is 18, 1. Of course, this is 18, 0, no double bond. 18 dot colon 0. And then what about this one? Now, this is linoleic acid. Linoleic acid, of course, has two kinks. Look at it. It has two double bonds. That means there's a kink here, and there's another what? Kink or bend. This bend, look, the first bend provides the first kink, the first double bond makes it to bend a little bit or a kink. The second one also brings even more kink. So look at this one now. This one has this one straight. But because this has two double bonds, it is even more bent. So this is actually more bent than this one. And like I said, this is also C18 carbon fatty acid, C18 fatty acid, and of course, it has 18 carbons and 2 double bonds. That is why it is actually more bent. And you can imagine, if you have more of these packing together, it is going to create a lot of space. So what it simply means is that if I want to grade the boiling and melting point of this, is that the melting point of this will be higher. This will have a higher melting point. Okay, let me say highest. This will have highest melting point, followed by middle. This will be in the middle melting point. And then, this will be the middle melting point. Let me say middle melting point. And this is going to have the lowest melting point. And the reason is because it has two double bonds. So the higher the number of double bonds, the lower the melting point of fatty acid, and the more fluid they actually become. So, well, let's talk about essential fatty acid. Now, essential fatty acids are those fatty acids that the body cannot naturally make. What it means is that they must be supplemented in our diet. So they cannot be synthesized within the body and must be obtained from the diet. And the common ones we're going to talk about here are the linoleic acid, which is otherwise called omega-6 fatty acid, which I saw earlier. This is, look at it here. Now, the omega comes from their hydrophobic end. Remember, this is the hydrophobic carbon end. If you count from here, 1, 2, 3, 4, 5, 6. Because this is in carbon number 6, we call it an omega-6 fatty acid. So counting them from the end is what gives them the name, the omega. So linoleic acid is an omega-6 fatty acid. And linolenic acid, linolenic, look at this, linoleic. This is linolenic, is an omega-3 fatty acid. So what it means is that if you are counting from the tail, from the hydrocarbon end, the first double bond is going to be at that carbon number 3. Now, of course, they are named according to the last double bond at the hydrophobic tail, like I just told you. And of course, what is the importance? They are used to produce icosanoid, particularly the body uses them to produce icosanoid. And icosanoid are the thromboxanes, the leukotrienes, and then the prostaglandins, which have important biological effect. They mediate a lot of biological responses in the body, including they affect blood pressure, blood clotting, immune and inflammation processes, and then even smooth muscle contraction. And of course, they are also used to synthesize other omega-3 and omega-6 fatty acid in the body. That is the importance of this one. So, since the body cannot make them, they are very, very much important. You supplement them from your daily diet. And you get them particularly from plants. They are usually supplied from plants and seafood. Plants and plant sources and seafood sources. Now, what about fatty acid notation? You see, now I talked about this already when I showed you the 3 fatty acids, the stearic acid. When I showed you this, now this is stearic acid, this is oleic acid, this is linoleic acid. When I showed you this, this is the notation we're going to be talking about now. Those fatty acid notation. These are the fatty acid notation. Now, so fatty acid notation indicates the number of carbon atoms and the number of double bonds in a fatty acid, and both of them are separated by a colon. A colon simply means dot dot. Remember that. That's what a colon is. A colon means dot dot. You know, this is colon, dot dot. Now, so example. What are the examples? 18.0 denotes 18 carbon saturated fatty acid with no double bond. And that fatty acid is actually the stearic acid. I already showed you that. And it's part of the ones you need to memorize in this class for your exams and quizzes. Now, the 18-1 denotes an 18 carbon fatty acid with one double bond. So, and an 18 carbon fatty acid with one double bond is linoleic acid, the one I showed you the structure earlier. It has 18 carbons and sorry, that's a mistake. I jumped the gun there. Okay, sorry. So I was talking about 18-1. So 18-1 means it has 18 carbon and one double bond, and this denotes the oleic acid. It has 18 carbons and one double bond. Now, 18 carbon and 2 double bond denotes linoleic acid. I also showed you the picture. It denotes 18 carbon fatty acid with 2 double bond. And then 18-3 denotes an 18 carbon fatty acid with 3 double bond. And here, this is linolenic acid. And of course, linolenic acid is what? Is an omega-6 fatty acid. Is the omega-6 fatty acid one of them that I talked about? Is an omega-6 fatty acid. And I'll keep writing that so that you guys will internalize that is an omega-6 fatty acid. However, just for the assessment, just for the exams and quizzes, you need to memorize the following acid, and that will be the last thing I'm going to talk about. I've already drawn them already and talked about them a lot. Just put your functional group and then make the squiggly lines with the shortcut to 18 carbons. If you count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it's 18 carbon. And I made the uniform. All these ones you need to memorize have 18 carbons. The difference is to know whether they have a double bond or not and the location of the double bond. The oleic acid is still, like I told you earlier, this is 18-0. This is 18-1. It has a double bond here. And if you count the double bond, it's the carbon number 9. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have to know this. This is oleic acid. Then linoleic acid has 2 double bonds. This is part of the one I showed you when I was telling you the effect of the double bond on their temperature and fluidity. I talked about this already. So this one has the double bond in carbon number what? Just like this one. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it has the carbon number 9 and 12, the double bond. So what you need to just know that most of them occur not as a trans, but as a cis configuration. So you have to put the cis configuration when you are drawing them. And the last one, of course, this is 18-2. This is 18-2, and this is an omega-6 fatty acid. And then the last one here you need to memorize is linolenic acid. The linolenic acid, of course, is an omega-3 fatty acid. It's an omega-3. I talked about this one. It's an essential fatty acid. Both of these two are essential fatty acids. Now, you have a double bond here. So you have a double bond in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it's 16, 17, 18. So this is where you have the double bond located. So linolenic acid is the notation will be 18, of course, 18, 3. It has 18 carbon and 3 double bonds. So your main preoccupation in memorizing this is just to know the location of this double bond. And these 4, since they have the same carbons, that you see they are very much easier for you to memorize, and you're going to be expecting some of these, particularly in some of the assessments. And having said that, we've come to the end of this lecture. Thank you for listening. Bye.